In this video, we'll see how to measure antenna S11 and analyze the signal received using some RF instruments. The equipment includes a signal generator, a network analyzer, spectrum analyzer, and two directional antennas. In this setting, the cable used is coaxial cable and the connector is N-type. These are the available observed frequency points, and in this video I'm choosing 1.3 GHz. Although the antenna is labeled 2.6 GHz, the 1.3 GHz measurement is still useful to observe how received signal behaves when antenna is operated away from its labeled frequency. So here's the setup to measure the S11 antenna. Before the measurement, one-port calibration is performed. The calibration standards used are open, short, and load. The purpose of calibration is to remove systematic errors from the VNA port, RF cable, and connector. Without calibration, the measured S11 may include cable and connector effects, so result may not represent the actual antenna input reflection. After calibration is completed, the antenna is connected to port 1 of the VNA using RF cable. The connector must be tightened properly to avoid unstable readings. After the antenna is connected, the S11 curve is observed. The markers are placed at the minimum point of the S11 curve. These points are the dips, not peaks, because lower S11 means lower reflected power and better impedance matching. The recorded VNA marker readings are as follows. For 1.3 GHz, the closest marker is marker 2. This is much lower than -10 decibels, so antenna shows good matching at this measured point. Reflected power ratio is calculated as shown. For -10 decibels, the reflected power ratio is 0.1. This means 10% of the input power is reflected, so about 90% of the input power is accepted by the antenna. For my S11 value of -31.69 decibels, the reflected power ratio is 0.000677. This means only about 0.067% of the input power is reflected, which means about 99.93% of the input power is accepted at this measured point. For part B, we use a signal generator to generate the RF signal. The output power is first set to -20 dBm. Next, we use the spectrum analyzer. We set the center frequency to 1.3 GHz, which is the same as signal generator frequency. The start frequency is set to 1.25 GHz and the stop frequency is 1.35 GHz. Therefore, the span is 100 MHz. Here's the antenna setup, which the distance between transmitting and receiving antennas is approximately 1.5 meters. The antennas are aligned directly to reduce alignment loss and polarization mismatch. The wavelength is calculated using lambda equals C/F, which gives a value of 0.231 meters. And to check whether the antenna separation is approximately in the far field region, the Fraunhofer distance equation is used. Using the panel antenna dimension as 0.4 meters, far field distance is 1.39 meter. So the actual antenna separation is 1.5 meters. Since it's greater than 1.3 meters, the measurement is approximately in the far field region. This distance is crucial because the received signal becomes more stable and the radiation pattern is more properly formed in the far field region. With output power of -20 dBm, the spectrum analyzer marker is placed on the received signal peak. The received signal is measured with power level of -47.619 dBm. Converting dBm to watts gives us about 10 microwatts. Increasing it to -5 dBm, the measured received signal on the spectrum analyzer is 33.961 dBm. Converting it gives us 0.316 milliwatts. Finally, at 0 dBm, it gives a received signal of -29.061 dBm, which is equivalent to 1 milliwatt. The result shows that the received signal increases when the transmitted power increases. When the transmitted power changes from -20 to -5 dBm, the transmitted power increases by 15 dB. This can be seen when the received power changes from -47.619 to -33.961 dBm. So the received power increases by 13.658 dB. When the transmitted power changes from -5 to 0 dBm, the transmitted power increases by 5 dB. The received power changes from -33.961 to -29.061 dBm, so the received power increases by 4.9 dB. This shows that the received signal follows the same trend as the transmitted signal. To measure link loss, we subtract received power from transmitted power. For -20 dBm, the loss is 27.619 decibels. For -5 dBm, the loss is 28.961 decibels. For 0 dBm, the loss is 29.061 decibels. We can also find the theoretical free space path loss using the equation, and we'll get around 38.24 decibels. The measured loss is different from the theoretical free space path loss because antennas are directional and have antenna gain. And to explain why received power is lower than transmitted power is because RF signal experience losses. One of it is cable loss, where signal power is dissipated in the RF cable. Connector loss occurs at connection points. Impedance mismatch occurs when antenna, cable, and instrument are not perfectly matched to 50 ohms. Free space path loss occurs because the signal spreads as it travels through space. Polarization mismatch and alignment error occur when the transmitting and receiving antennas are not perfectly facing each other. And lastly, the environmental reflection occurs when the RF signal reflects from nearby objects such as table, walls, instruments, and metal surfaces. Also, at 1.3 GHz, additional mismatch may occur because the antenna is labeled for 2.6 GHz operation. Some of the precaution worth considering is signal generator should start at the lowest power level, which is minus 20 dBm, to protect the spectrum analyzer input. Maximum input power of spectrum analyzer must not be exceeded. The RF connectors must be clean and tightly connected, and cables must not be bent sharply because this can increase cable loss or even damage the cable. The antennas must not be touched during measurement because touching the antenna can change its impedance and affect the received power. The antennas must be placed facing each other to reduce alignment loss. And lastly, the antenna distance should be kept constant at 1.5 meters, so received power comparison is fair.